The first reaction we're going to talk about in the reactions part of this chapter is going to be preparation of aldehydes. Now we're going to prepare aldehydes as we discussed in the alcohols chapter by oxidizing primary alcohols. So we can do that with a chromium compound like pyridine and CrO3, but remember this has to be cold. And we can do this with pyridinium dichromate, or in the last chapter we talked about CC, pyridinium chlorochromate. So those are a couple possibilities. And we do that oxidation, we are going to take this bond here, we're going to take a hydrogen from either side, and we're going to oxidize it to form the aldehyde. Remember, this is unstable, and will oxidize very quickly under normal conditions to give you the carboxylic acid. So you have to be very careful, remove it immediately, and try to keep that aldehyde is very difficult. Ketones, however, are prepared from secondary alcohols. It's going to be very easy, or much easier to get the ketone and keep the ketone. And we can use potassium permanganate, KMNO4. Again, we can use CrO3 and pyridine. If it's a little bit warmer, or if you just wait a little while, that aldehyde will oxidize to the carboxylic acid. Any of the Jones reagents, like we discussed in the previous chapter, this is just a bigger definition written out for you. I probably should move that to the other chapter, but we talked about these. We used a lot of K2Cr2O7, or we can also remember say that this is just a cation. We can throw sodium in there as well. So that would look something like this. This is cyclohexanone is what we're going to get, but right now it's cyclohexanol. I can write today. So we're going to take cyclohexanol and we're going to change it to cyclohexanone by removing a hydrogen from here and one of the other fronts from the carbon. So this is going to be our product here. We get cyclohexanone. So the oxidation is going to remove 2 hydrogen atoms and form that carbonyl group that we're looking at. Now, once we have a carbonyl compound, what kind of reactions do we undergo? So the 2 reactions we just discussed were a review of the alcohols chapter where we formed the carbonyl compound. Once we have a carbonyl compound, we can undergo oxidation or addition. Oxidation and reduction, aldehydes are going to be very easily oxidized. Remember, they're easily oxidized to carboxylic acids. We know this. Aldehydes and ketones can be reduced back to the alcohols they came from. What is the aldehyde? It's going to give us a primary alcohol, and a ketone is going to give us a secondary alcohol. This is where they came from. Back to their roots. Now, we can also add hydrogen, so we can reduce this. This would be a redox reaction back to an alcohol. We can react them with alcohols to give what's called a hemiacetal and acetal if it comes from an aldehyde. A hemiketal or a ketal if it comes from a ketone. I think they're moving now to calling all of them ketals and not being as specific into the acetal, but I'm going to continue to be specific through this, and I want you to be as well. So aldehydes and ketones can also react with each other to give what's called an aldol reaction, which is also known as a beta hydroxyl carbonyl product. So we're going to go through each of these. First up, oxidation of aldehydes. So oxidation of aldehydes, this is going to be a very easily done process. Remember, all you have to do is let it sit or use something other than one of the 3 special reactants to get this reaction. So any of the multiple oxidizing agents, we're going to react this and we're going to put another oxygen in here. So we're going to see this carboxylic acid. Now, liquid aldehydes are super sensitive. They're, oh, sorry, I was going to name these for you. Hexanal, because 1, 2, 3, 4, 5, 6. This will become hexanoic acid. We'll get to that in the next chapter. So hexanoic acid because it's a carboxylic acid. Now, liquid aldehydes are super sensitive. If we were doing lab in the actual lab together, we would do this one and you could see the reaction happen during the lab, that the oxygen in the air can actually oxidize this compound because they're so sensitive. So you have to be careful about oxygen in the air when you're storing this product. So this is benzaldehyde, and it's going to react with oxygen just in the air to form benzoic acid. So benzaldehyde forms benzoic acid very easily. How do I know if an aldehyde has been or can be oxidized to do this? So, well, there's a couple of visual tests for the aldehydes, and it's based on easy oxidation. So how can I tell if I have an aldehyde? I'm going to try one of these, and the first one up is called the Tollens test. And the Tollens test forms an actual silver ion. There's a silver deposited on the outside of the test tube or on the outside of the flask, and it produces a silver mirror. It's fun. I usually do it for you, at least as a demo. In this class, we would usually make it, so hopefully you'll get a chance to at least see it at some point. But you form a silver mirror on the inside of the test tube or the flask, and you can actually, it looks just like you're looking in a mirror. Now, Benedict's test is going to take the copper ions that are in the Benedict solution, that's in a basic solution, and they're going to be blue to start with, and then when you react it, if there's an aldehyde present, it produces a brick red precipitate. So you'll see this brick red come crashing out of solution. So let's take a look at a couple of these. Here we have an aldehyde reacting with KMNO4. We have an aldehyde reacting with a Jones reagent. And here we have the Tollens test. So this would be another reagent that would give you, so for the Tollens test. So what would happen to this one? We're going to oxidize it and we're going to throw an oxygen in here to get that carboxylic acid. So here we had 1,2 ethanol to produce ethanoic acid. Here we have benzaldehyde producing benzoic acid. And here we have propanol, 1, 2, 3, producing, this one is negatively charged. It's not an acid in this case. So in this case, we have a basic solution. And in a basic solution, we don't have extra hydrogen ions around to protonate that. So it's going to be deprotonated. So it's actually going to be an ion, and the silver mirror is going to be the silver solid that's produced from this reaction. So this is where the silver comes from, is from this reagent here. So you would see a silver mirror produced. This is oxidizing aldehydes happens all the time in nature, so you're going to see this a lot. So let's take a look at a reaction that might happen naturally. So we can actually use copper ions again in the Benedict's test. This is going to be something that we do. We do this in the medical field sometimes. You can do this to test for ketones in urine. We can do this for, because even though we can test for aldehydes, we actually test for ketones, because if a ketone is present, you can usually readily make an aldehyde, and we'll discuss that further in a little while. But here we have an aldehyde, so we can just talk about the aldehyde right now. The aldehyde is going to react. Again, we have copper ions in a basic solution. So as we're going to get this oxygen put in there, like we see here, but it's a basic solution again, so it's not the carboxylic acid. It's going to be the negative ion, the unprotonated, or I should say deprotonated form. And this is our brick red precipitate. So this can be used to test for what's called reducing sugars. It's going to be something that we're going to focus on when we start getting towards our biochemistry chapters. So that is oxidation. What else can we talk about? Well, reduction. So let's talk about reducing that carbonyl. So when we want to reduce that carbonyl back down to an alcohol, people do this all the time to make your sugars not count as sugar. They'll count as sugar alcohols, and then they give you all sorts of digestion issues. So the carbonyl group from our aldehyde or our ketone can be reduced back to an alcohol by adding hydrogen. Now, if you remember back, adding hydrogen in the presence of one of our transition metal catalysts is going to make this go much faster. So we also have to add, so we're going to add the transition metal catalyst on top of the hydrogen. So here we have hydrogen and platinum reacting. We're going to reduce this back down to a single bond and a hydrogen. So we're going to add a hydrogen here and a hydrogen here across the double bond to get back to an alcohol. Since it was a ketone, it'll be a secondary alcohol. So here we have the ketone version, here we have the aldehyde version. We're going to get a hydrogen across both sides, and we get the products. Here's the secondary alcohol from the ketone, and here we'll see the primary alcohol because it was an aldehyde. Pretty straightforward reaction, just adding hydrogen across that double bond. The only problem with adding hydrogen in this way with a transition metal catalyst is it does not discriminate. So if we had a double bond somewhere and we added hydrogen with, platinum or something like that, we would reduce all of the double bonds back down, just like we talked about in our alkenes and alkynes chapter. So they would get reduced back down as well as this one would also go down to an alcohol. So we would see that be CH2 instead of just H2. Let's have you pause it and predict the reactions, the results of these reactions. So predict the products. I'm going to keep tripping over my words all night, I guess. So we're going to add a hydrogen. Pause it, please, and try it. Add a hydrogen across the double bond, so we'll get one here and one here. We end up with this product. So here we have 1, 2, 3, 4, 5. We have pentanal reacting to produce 1, 2, 3, 4, 5, 1 pentanol. So backwards, we just learned this reaction the opposite direction. We learned it, right? We learned it this way in the alcohols chapter. So on the bottom, we have a ketone. Ketone's going to add the hydrogen just like we did in the aldehyde with the transition metal catalyst. We're going to go across and we're going to react to form the alcohol. So here we have cyclopentanone on the left, and on the right we have cyclopentanol. So the most common laboratory reagent for reducing an aldehyde or a ketone is actually sodium borohydride or lithium borohydride, some type of borohydride. So this would be Li plus BH4 minus. This is the anion borohydride. Okay, this is the important one that I was just describing, that it's going to reduce this down to an alcohol, but not reduce the double bonds. And that's a lot of times what we're looking for. It's selective. So it does contain a hydride anion, and it only removes the carbonyl group. That pi bond, it's going to reduce it to an alcohol. But with our metal catalysts, all the pi bonds, it's not selective. It's going to get reduced. So this one is preferred. How does it happen? Why is it selective? Let me show you. Okay, so you don't have to draw this for me, but that hydride anion is going to be attracted to those pi electrons on the carbon here between the carbon and the oxygen. These electrons are going to come back out onto oxygen, and we get this alkoxide ion. We then have an acidic water in solution here. That water hydrogen is going to add here to form this OH group. This is where our alcohol is coming from. And we add the other hydrogen here that we see. This is still our hydride. This came from here. So this is where the other hydrogen comes from. So let's take a look at that general reaction in an actual compound. So here we have our ketone. I can just do the laser pointer, I think. Here. So we have our ketone. That ketone, the hydride is going to be attracted. I'll just draw it back. Be attracted here. It's going to react at the carbon. We add that hydrogen in. We now have an O minus. It's got that extra pair of electrons that we saw here. And then it's going to take that extra hydrogen from water and it's going to add it to form the alcohol. Pretty simplistic, but it does not affect any of the other double bonds that are around. It's only selective to that carbonyl compound. This is really important in biological systems, and it's actually one of the common reagents that you've probably memorized. NADH, NADPH, these are all going to be electron carriers in our system. So they're going to pick up electrons as they go through reactions, and then they're going to bring them to the electron transport chain where we produce all of our energy. So these are going to carry electrons through our system. So let's take a look at pyruvate being reduced down to lactate. So this is something that we'll see in glycolysis. Okay, I know you want to. All right, so here we have pyruvate. The hydrogen here, this is our borohydride kind of thing that we've been talking about, that H hydride ion that we're talking about. Okay, this hydrogen is going to be coming into the carbon, and we're going to get those electrons back to the oxygen. Here's our hydrogen we added. We now have the minus sign. The acid comes in here, and we get this alcohol group. Easy peasy. All right, so adding a molecule of alcohol is up next. This one tends to be a little bit more confusing for people. It's got a few more steps, and there's a bunch of alcohols that seem to just come out of nowhere. Where did they come from? So you're going to want to reread this one a couple times in the chapter. Maybe rewind the video, go through it a couple times. Definitely practice it. So when we add an alcohol, it's actually a really simple addition, but just for some reason is confusing. We're going to add a molecule of alcohol to a carbonyl group for an aldehyde or a ketone. If it comes from an aldehyde, it's a hemiacetal, or a half. Hemi means half. If it comes from a ketone, it's a hemiketal, or a half a ketal. Hemiketals are regarded as a subclass of hemiacetals. So they can call them all hemiacetals, like I was saying earlier, but I'm going to stick with being specific. So hemiacetals that have R groups that are not hydrogen is what they're considered. A hemiacetal functional group is a carbon bonded to one OH group and one OR group. So a carbon bonded to one OH group and one OR group. We'll see this, don't worry. How do they form? The hydrogen that's on the alcohol is going to add to the carbonyl oxygen. So if we have the CO here, it's going to add to the oxygen. And the OR group is going to add to the carbon. So we're adding directly across that double bond just like we did before. Hemiacetals are unstable and are only a minor component of our mixture when it's in equilibrium. So we're going to see the acetal and the hemiacetal. You'll see it preferentially add twice as opposed to just adding once. So here we're going to say we just have one of these, okay? So what happens here, why do I have it drawn like this? Because if you draw it like this is our OH group. Now we would normally have it written like this, right? But by drawing it straight up in the air like that, we're able to kind of do something like this. Use your imagination. This isn't exactly, I just want to be clear, this is actually not the hydrogen that's doing this, but that's okay. You can picture it this way. So this hydrogen goes there, this bond breaks, and this adds here. So this is our product, I think. There we go. Come on, product. All right, here we have our COH, which is also bonded to OR. So this is our R group. ROCOH is a hemi. Here we have a ketal, so we have an aldehyde here at the top. Here we have a ketone at the bottom. We're going to get that same reaction. This gets the hydrogen, this gets the oxygen, bond breaks, and we end up with this product. This is a ketal, a hemiketal, a half of one, because we still have a hydrogen here. What's the difference in the molecules themselves? How do I know it's a hemiacetal or a hemiketal? This right here. So this tells me it's an aldehyde. It came from an aldehyde because there's still that hydrogen there. It's important. This R group means it came from a ketone. Now this is a hemi because there's not an R group here. This is a hemi because there's not an R group here. What happens when we react this again with a second aliquot of alcohol? So if we add a second one, I'll show you what happens in a minute. Let's first do this one. This is benzaldehyde. We're going to get a bond here and a bond here. We're breaking these ones. So we end up with a hemiacetal. Here's our OH. Here's our OR group. So this is our OR. And then this is our hydrogen saying that it was an acetal, not a ketal, because of that hydrogen. And it came from an aldehyde. So why an alcohol and a carbonyl functional group are in the same molecule? If they are, they can actually do this reaction by themselves. And guess what? This happens a lot in our bodies with our sugars. So the cyclic structure of these tend to be more stable. So they generally exist in their cyclic structure rather than their hemiacetal form. So here we have an aldehyde and an alcohol functional group. They need to be far enough away that they can form a ring that's not going to be super strained. But what happens is they rotate. So this is just a simple rotation where they come near each other. Now we have our alcohol. The oxygen is going to add to the carbon. This bond is going to break. This bond is going to break. The hydrogen adds to the oxygen, and we get our hemiacetal. But now it's in a cyclic form. So this happens a lot in nature with our sugars in our body. So we'll see this again, don't you worry, but you're going to want to definitely study up on this reaction so you can be familiar with it. So aldehydes and ketones can react with two aliquots of alcohol, so two molecules of alcohol to form a full acetal or a full ketal plus water. So the reaction has to be acid catalyzed because this hydrogen is technically coming from the acid. So here I have the OCH3 and a hydrogen. If I were to do this like I was doing it before, I would have this written up and I wouldn't have that hydrogen there. This is going to happen first. And then we react it again. So first we see, come on, oh, we see that reaction. And then, so I'll just draw it out here. 1, 2, 3, 4. So we go down to the OH, OCH3. Then this reacts again, and you're going to see this hydrogen go away, and we're going to see the OCH3. But the way this happens, I'm going to show you the, excuse me, the mechanism of this reaction. I don't know what's going on with my brain tonight. The mechanism of this reaction in just a little while. Okay, so let me erase that. So we're going to get two ether groups. Here we have one. This is our original one. So we have the original addition would have been this one, OCH3, and we had OH before. Now we're removing that H and we're getting the OCH3 because it's going to be whatever's on the other side of the alcohol. These are going to be matched. So whatever, this is the alcohol group minus the hydrogen. And then in the end, we're also going to get water as a byproduct. Here, the ketal, again, the same reaction. The only difference here is this one has a hydrogen and this one has a methyl group. So the top one is an acetal because of the hydrogen. This is a ketal. Acetyl, ketal, I don't know, however you want to say it. Tomato, tomato, doesn't matter. So how is this happening? I'm going to show you the whole mechanism. If you don't like mechanisms, you'd make you run screaming, then run screaming or fast forward or whatever you got to do. So step one is we add the proton. This is from the acid. Remember, this is acid catalyzed. So we're going to have this acid in solution. The electrons on the oxygen are attracted enough to that acidic hydrogen that they're going to grab it and form this bond. Then the electrons from the pi bond are going to want to relieve this positive sign. So they're going to donate the electrons back to the oxygen because oxygen is more electronegative. It breaks this bond and the plus sign goes on to the carbon because carbon can handle it. The carbocation is more stable than an oxygen cation, but still not very stable that it would like to stick around. So we want to relieve this carbocation. Now, the words that I have written on the slide, add a proton. Adding a proton to the carbonyl oxygen makes the carbonyl oxygen a stronger electrophile and more susceptible to an attack by a nucleophile. We haven't really been using those words, so don't get too caught up in them. It's all good. Just look at the pictures. Let's follow what's going on. So now we have this plus sign here we want to get rid of. We have an alcohol that's floating out in solution. That's going to be our solution to getting rid of that plus sign. So here, the alcohol group, the oxygen, is attracted to the carbon, the carbocation, I should say. All right, now we have this bond that forms between the oxygen and the carbon, and we have another plus sign on the oxygen. Well, oxygen doesn't like that, but this is not a very good leaving group on its own, so it's going to reorganize, and it's going to move the hydrogen up here to form water. We don't talk a lot about leaving groups, but water is a better leaving group, so it's going to do that. It's going to rearrange itself. So we're going to do a proton transfer, it's called. We're going to transfer a proton up to here, and it's going to now have this group that looks a whole lot like water, but with a plus sign right now. So that water can leave, and when it does, it leaves a carbocation. So the water is going to get kicked out, it leaves, and we leave that carbocation, which then needs to be filled. So we're going to do that. We leave the water, so the water leaves. Bye, water. Well, it's an aqueous solution, so there's water all over, right? Okay, now we have a second alcohol molecule that's going to come in and relieve that carbocation. So here's our second alcohol. The electrons on the oxygen come over and they're going to be attracted to that carbocation. Now we have this CO bond again. The hydrogen is going to donate the electrons back here to relieve this oxygen cation, and the hydrogen is going to leave as the hydrogen ion that we started with. So we have to replace that one as the catalyst. So it does. It replaces the catalyst, and we're back here. We have ROCO R, ROCOR with 2 methyl groups on it would be a ketal. Easy peasy, right? Nothing to it. Well, realistically, there's nothing to it because I'm not going to ask you to draw the mechanism. Since I'm not going to ask you to draw the mechanism, if you can see where you can write this OH group up like this is actually a hemiacetal already. So what we're going to do is we're just going to add, this one goes here, and we go off and form water. We leave this opening, the oxygen comes in and adds to the carbon. Whatever else is here just gets added on the other side. So I do want you to be specific that this bond goes between the carbon and the oxygen. That's important. This is an acetal because it has the hydrogen there. Here we're going to get this one that goes and forms water. The oxygen comes in, bonds with the carbon, and we get here, this is actually a ketal because we have ROCOR, but then we have R groups on either side. There's no hydrogen, so that's a ketal. So remember, hemis are unstable. So hemiacetals and hemiketals are both unstable. They only exist when we're in equilibrium with the acetals and ketals. All steps are reversible, so that's important because your body is going to be doing these. And cyclic hemiacetals and hemiketals are much more stable, especially those with 5 and 6 membered rings because they don't have as much strain as, say, like a 3 or 4 membered ring. Acetals and ketals are very stable in neutral or basic solutions, but quickly break down in any amount of acid because they are acid catalyzed reactions. So that makes a whole lot of sense that they're going to break down if we put them in an acid. All right, so this is glucose. Hi, glucose. Glucose forms a relatively stable cyclic hemiacetal by reacting with itself. So here we have our OH, and here we have our aldehyde. The oxygen is going to form a bond to the carbon. This one's going to go to the oxygen, and we're breaking this bond and this bond. So this is our, let's see here, oxygen, carbon. So we have our R, O, C, O, R, R, O, C, O, actually H. I wrote R, should be H in this case. Doesn't always have to be, but because it's glucose. So it's a hemi, and it has a hydrogen here, so it's an acetal. Glucose, ribose, fructose. Well, fructose is a combination of those, but well, anyway. We'll talk about it when we get to the sugars and the carbohydrates. We'll be there soon. But this is how we form them. We can actually hydrolyze them. Remember, they're all reversible, as many of our body reactions are. So we can actually go backwards as well, which is why this has a double barbed arrow. So let's talk about what's called hydrolysis of hemiacetals or ketals. So in the presence of an acid, they can go forward or backward. So what will happen is we'll see this go this direction and break it down instead of going to the forward reaction. So we'll see it reverse back on itself. And what happens is we can go both directions, right? So we can go forward or backward. In this case, this is the reaction we want to talk about is going to be the forward reaction. So we have what here? We have an acetal and we have a full-on acetal because I have R, O, C, O, R group. So what's going to happen? I react it with water. This is a hydrolysis. Lysis means to break, right? So I'm going to break that off. My alcohol groups that are going to come off are going to be this whole thing plus hydrogen. So it's going to be HOCH3, which is why you see that written there. And we're going to break both of these off. So we get the second HOCH3, and we get our aldehyde back. Here, going in the forward direction, we're going to break off. This is a hemi, right? So I have HOCOR, ROCOH, because I have the OH, it's a hemi, and it's an acid, it's a ketal. It's a ketal, because that's an R group. Let me erase that because this is getting really bulky on this side. A lot of red. When we do that, we're going to take off the OCH3, so this goes away, plus hydrogen, to form back this alcohol, and we get our ketone back. Now sometimes we can actually have a ketone and then something that forms what's called an enol. We mentioned this briefly before, where we have a keto-enol tautomerization, it's called. So we have this ketone here, our carbonyl group. Then we have what are known as alpha carbons, the ones right next door. On those alpha carbons are alpha hydrogens. Okay, so what happens is they're going to tautomerize. And tautomers, the term tautomers, means they're isomers which differ in the placement of a hydrogen and a double bond. So this is going to move around. And let's say a hydrogen comes up. See, we get an OH instead of a double bonded oxygen. And now we have a double bond, one less oxygen. So instead of being CH2, it becomes CH. And we have our CH3. So this hydrogen goes up there. We break this bond, and it comes and forms a double bond here. Or this side. So either way, either of the alpha carbons. The keto form has a C double bond O. That's the keto of the keto-enol. And the enol form has an ene and an ol. So an ene, a double bond, and an alcohol for the ol. Enol is derived because we have an alkene and an alcohol. The keto form is usually the most stable. That's important to recognize that that's going to be the most stable. So more stable, less stable. All right, I would like you to pause it and try it, please. Draw what comes after this. So what happens here is, I want you to pause it and try it, please. We can get an ene here, or we can have an ene here. This one, this is an alpha, and this is an alpha. This goes to an OH, and we can have one here. Or here. Now we can also have cis and trans isomers of those as well for this enol, because of the way that, sorry, not for this one, but for this one, is what I meant to say, sorry. Drew a whole big circle and then looked at what I did. All right, so we can have cis and trans for this one because of where it is. But actually it'd be more E and Z, but anyway, never mind. We're not going to go that far into it, okay? Now, one more thing, I just want to remind you of all the functional groups we've been talking about, so I want you to look at these. Oh, sorry, those are the answers. Here are the structural formulas for two steroid hormones, cortisone and aldosterone. I want you to name the functional groups that are present in each. So this is just normally in class where we would practice naming some functional groups like, alcohol. This is a ketone, I think, yeah. This is a steroid. In this particular order, this is a steroid. And this one, you see that backbone? 3 6-membered rings and a 5-membered ring. This is a ketone. Let's see, what else do we have here? Another ketone. Kind of boring. These are a ketone. Ketone. Finally, an aldehyde. And we have an alcohol. 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 I don't know if I'm spelling these right. All right, so that looks good. These are some of the reactions that we talked about just as a summary slide. There you go. That's the end of this chapter.